So we will now start on the Gauss-Seidel power flow method. The first way to solve the power flow equations. We will start with go straight very fast into an example. But here you can see like just a two-bus system, and we can call the bus 1 as a slack bus. That means that we want to calculate at the bus 2 now in this case. So here is this here is the equation I've seen before, how you define the power flow problem. And we can then from this use the following. We now start, now I is 2, so it means P2 minus JQ2 divided on V2 equals Y21 V1 plus Y22 V2. And of course, if you have been more buses, it will just continue to Y2 Vn. Yeah, but now we just see here. So we have defined on this fashion. Then we can further calculate it like this. We have V2 voltage 2 will be 1 divided by Y22 P2 minus JQ2 V2 complex conjugate minus Y21 V1. Yeah, and of course if you have 2, 3 and so on, but actually it will just be like this here now. Like this. So you then use these schedule values on the reactive power. And of course V1 here is known, it's a slack bus. And V2 you just start with a flat start, as I said up here. And then you calculate this equation and you get a new value of V2. And you put this into here and you recalculate until you are satisfied with your solution. The admittance you of course have already calculated previously. I think we go straight into an example, and we can take it from there. Maybe it's easier to see when we have some numbers. So example, let's draw a system. Like this. This. So we call this for S load 1. S load 2 equals 1.0 J0.5. This V1 equals 1, and then we have V2 is equal 1 angle delta. Then we have the S generator 2 at that bus 0.25 plus JQ32. Maybe let's use capital Q32 like this. This is the S generator 0 generator 1, and we have an impedance between 1 and 2 of 0.5 like that, and we define this as the slack bus. So we will have a couple of loads we need to find. We have these two buses, and on this bus here, we know there's a load connected. That is actually defined how much is in per unit, but we don't know the angle in that bus, and we don't know how much reactive power that is necessary from the generator. So this is things we have to calculate. So we start with the admittance bus, as we had done earlier. This will be a very small one. So the Y bus equals Y11, Y22. There are two buses, so it's 2 by 2 matrix. Y21, like this. And actually this matrix, the values will be the same, just by a plus and minus value. Let's do this. J 2.0 minus 2.0 minus J 2.0 J 2.0. Just take the inverse of the impedance above. So that's actually the all we need for this small system. Let's then calculate the voltage first iteration. So we start here, and we have then the V2 first iteration divided by Y22, V2 schedule minus JQ2 schedule divided by V2. And this is iteration like 0, as this was 1. Let's see. And then we have minus, let's say minus, we have a Y21 V1. Like that. And then we can start to put in numbers. 1 divided by J 2.0. And then we know that P2 is 0.75 plus. We then use, don't know, so say 0. And as default, I'm using flat start, 0 angle, 1 per unit, minus 0.0, 0. Let's start first iteration, and we calculate then a value of 1.068 minus 20.556 degrees. Could also then from this have calculate the angle from this relationship. The cotangents, we have the imaginary value of V2 01 divided on the real value of V2 01 minus 20.55 degrees. What we actually do now is that we take this value here, and we force it to 1 0 per unit, and we calculate again. Because the first calculation is based on this flat start, we don't know, but now we have a new angle value that we can use further. We also now calculate the Q2 of iteration 2 of iteration 1. And to that we take the minus imaginary value of the whole expression, v2 of 0 complex conjugate times y2 1 v1 plus y2 2 v2 of 1. This becomes minus 0 1 angle, oh sorry, do that again, 1 angle now it becomes right, I think, minus k 2.0, so that's yeah, times 1. This equals 0.1273 per unit. So then we have a value for the reactive power, iteration 2, and the voltage, iteration 2. And then, iteration 1, sorry, and then we can calculate for iteration 2. Let's do that below here. Now, then we write v2 2 equals then 1 divided by 2.0 times 0.75. And now we have the reactive power. We already calculated 0.1273, 1273, like this, divided on angle 20.556 minus 2.0 times 1 angle 0, like this. So just remember that on this bus, let's go up to the future, we are providing then the 1 per unit voltage at the second bus here, because the generator could always control that voltage. If it's within, of course, the constraint of the machine, it can do that. That means we are then providing the voltage here, length for the V2 in this way. So now you see that we're using this Q2 value into the new iteration, and also the voltage here. And then we get the value of the calculator. We get 1.0003 angle minus 21.9. That's the new voltage. Like here. And then you do the same. We now calculated Q2O2. it gives this value for reactor power per unit. The second iteration. First you had 0.1217, now we have 0.1446. And then you continue until some kind of criteria is met. And if you do this same here, you get something like 1.00014, the angle of minus 22.0153. And then you calculate K2 and 3. So, and you understand very fast it becomes computer calculation. Takes 2, but typically you should try to do like 2 or 3 bus system by hand, so you know how it works like this. So now you can, in Canvas, we have then put out this example with the MATLAB script. So you can go in Canvas and run M script and try to understand. So then you can use those M scripts for more advanced systems if you have exercises and assignments. One thing also these scripts are calculating is the line loss. I also talked about that briefly before, but I think I will take it again here, more detail, so you know what's going on in this calculation. And let's draw this what I call a pi equivalent line model like this, and we have something below here. And then you have let's see, we call this for, let's take another color, VI, this for VJ, so it's node I and J. And then you have a current here called IJ, and you can also define a current I that is JI, opposite. So this denotation has a meaning for the direction. Further, we have Yij, the admittance of the line, and you can have Yi0 and Yj0 like this. Then we can put on some currents. Let's take, we can call this for IL for line current. Then we can have a current going here, I0, and we can have a current going here, Ij0, like this. So if we then take from I to J as a direction, we can write is equal to IL plus I0 equals Y let's see, just take this again. This is the VI. And from the J to I, opposite, we can write current Ji equal minus IL line current plus Ij0 from the right hand side equals the admittance J minus Vi plus J0 and VJ. So this is the line current, you see. This is represented by what's happening on the iBus node to ground. And you get then, of course, this minus also for the opposite value. Then we can, from this, we can actually calculate the complex power S. Now the omega is J equals VI J complex conjugated and opposite SJI equals VJ current now JI complex conjugated. So you can calculate at each side of this line like this. So if you then go over to call it, let's say plus 1 and 2, if you call this for plus 1 plus 2, we can actually then write, let's use here, S1 2 is equal to V1 1 2 to V1 times divided by the impedance between V1 minus V2 like this, and S21 and calculate V2 I21 equals V2 by set times V2 minus V1 like this. So of course the computer program will calculate this for all of the nodes in the system, so you can have the line losses both for active and reactive power. And if you have the complex power, you can just take the imaginary and the real value of this. One thing I maybe forgot to say, if we go up again to this, let's see, here, this diagram, and you can see that the S load 2 have 1 per unit of load power, and we have generator that's producing. So you see that from here we can calculate a value of 0.75, and that's why we use that value when you calculate it in here. So you have to keep track what is defined as load and what is defined as the generator power.